Good morning to all. Our topic is about biomaterial. Our team consists of Vighnesh and Ramees. This is the introduction slide. A biomaterial is a substance that has been engineered to interact with the biological system for medical purpose, either a therapeutic, treat, augment, repair, or replace a tissue function of the body, or a diagnostic one. Metal biomaterials are used for fabrication of many types of medical implants. Example: joints, bone, prosthesis, or orthopedic screws, nails, pins, and other fixation elements, stents, dental crowns, etc. They are suitable for load-bearing application because they possess sufficient mechanical strength and ductility. Corrosion-resistant materials such as 316L stainless steel, copper-based alloy, and titanium-based alloy are most of the widely used metallic biomaterial. Type of biomaterial. First one is metallic-based biomaterial. It was considered that it has far superior corrosion resistance to any metal at that time. Since then, metal has been used widely as biomaterials. The demand for major biocompatible metals such as stainless steel, titanium, chromium, cobalt, nitinol, gold, and silver. Second one is the polymer-based biomaterial. Polymer-based biomaterial have replaced other materials such as metals, alloys, and ceramic because of their low cost, chemical stability, easy processability, and reprocessability, and better corrosion resistance. The polymer-based biomaterial have been extensively used in medicine, biotechnology, food, and cosmetic industries. The third type is the ceramic-based biomaterial. The bioceramic has certain properties such as stiffness, hardness, chemical stability, and resistance, among others, that make them highly biocompatible. Some of the advantages of the bioceramic include biocompatibility and bioactivity, less stress shielding, no disease transition, and easy availability. The only disadvantage is the brittleness of the material, which is set back in local load-bearing application. The next type of biomaterial is natural biomaterials. Biomaterials are classified into two main groups, namely synthetic and natural biomaterials. Synthetic biomaterials are classified as metal, ceramics, biodegradable polymers, and biodegradable polymers. The disadvantage of synthetic biomaterials such as difference in structure and composition, biocompatibility, and low ability to induce tissue remodeling are overcome by natural biomaterials. And then the next type is the inorganic glass-based biomaterial. Inorganic glass is an amorphous, hard, and transparent liquid formed after the supercooling process. This class of biomaterial comprises silicate, phosphate, and bioactive glasses. Inorganic glass is usually manufactured by fusing a mixture of multiple metallic silicate. It is referred to as an inorganic glass because glass is a combination of inorganic compounds such as silicate, sodium, potassium, calcium, and lead. This type of biomaterial is regenerative biomaterial. Regenerative biomaterial find their major application in tissue engineering, which is driving the regenerative biomaterial market. Tissue engineering products consist of marginally manipulated biomaterials and cells. Earlier, regenerative biomaterials were used only in prosthetic devices. Still, they are being used in the bone, liver, cornea, cardiac tissue engineering, wound healing, tissue engineering, blood vessels, and the development of biomaterial scaffold. Then the next type is hybrid biomaterial combination. Hybrid biomaterial combination are a combination of natural derived materials and synthesis materials. Biomaterials are widely used in application of tissue engineering such as in scaffolds for regenerative medicine, nanomaterial for biosensing, and tailoring of an inorganic nanoparticle as they shape and structure the tissue, providing the mechanical stability and the strength. In this slide, we are discussing about titanium and titanium alloys. Titanium and titanium alloys are relatively inexpensive structural materials used in offshore industry, chemical industry, aerospace, and automotive industry as well for luxury goods and medical devices and implants. For medical purpose, advantage is taken of all specific property of titanium: high specific strength, high corrosion resistance, low stiffness, and excellent biocompatibility. The low elastic modulus compared to surgical steel is beneficial for reduction of the so-called stress shielding effect in the bone implant. Magnesium alloy powder metallurgy manufacturing of shaped magnesium implant, for example, a metal injection molding process, and also is used for surgical implant considering their excellent biomedical application. The introduction of functional porosity would support the primary fixation and the degradation of magnesium implant by enabling the ingrowth of bone cells. osseointegration into the degrading implant. Generally, magnesium alloy provide elastic modulation and strength matching those of bone tissue, reducing the risk of stress shielding to a minimum. The corrosion behavior of magnesium in the body fluid permit well-controlled degradation of the material. Nitinol alloy. The shape memory effect is the pronounced in nitinol alloy which are based on the intermetallic phase nickel titanium. The importance of the shape memory alloy SMA for biomedical application has increased significantly in the past few years. These alloys can return to their original shape even after they have been deformed well beyond the elastic deformation limit. Pseudoelastic shape recovery is the basic principle of self-expanding stents for treatment of embolism. If shape recovery is inhibited, a well-defined permanent load remains. The function of orthodontic wire is based on this effect. The production of complex shaped components from this alloy has so far been limited by the fact that machining them is very difficult and expensive. Powder metal is an alternative production method which enables near-net shaped components with complex geometry to produce from nitinol powder with less loss of material. Okay. Powder metallurgy. The main advantage of powder metallurgy product is that they contain porosity which compromise their mechanical property closer to those of human bone. This, this enhances the healing process. Moreover, the pores may be also impregnated by drugs or growth factors which are eluted during healing. The presence of pores smaller than 100 micrometer is also advantageous because it increases roughness and enhances addition of proteins and cells to the surface and improve osteoconductivity as a consequence. Powder metallurgical method for biomaterial fabrication. The first one is conventional powder metallurgy. Second one is hot isostatic pressing (HIP). Third one is spark plasma sintering (SPS). Fourth one is reactive sintering. Fifth one is self-propagating high temperature sintering (SHS). Sixth one is impregnation of polymer formed by metallic slurry. Seventh one is forming of metallic powder. Eighth one is space holder technique. Powder metallurgy method for biomaterial fabrication. The first one is conventional powder metallurgy. Second one is the hot isostatic pressing (HIP). Third one is the spark plasma sintering (SPS). Fourth one is the reactive sintering. Fifth one is the self-propagating high temperature synthesis (SHS). And sixth one is the impregnation of polymer formed by metallic slurries. And seventh one is the forming of metallic powder. Eighth one is the space holder technique. This technique will be described by the coming slides. Conventional powder metallurgy. Conventional powder metallurgy consists of two basic steps: cold combustion and sintering. Cold combustion may be performed uniaxially or isostatically. The obtained green compound is subsequently sintered at elevated temperature. As the temperature diffusion and other mass transport mechanism take place, leading to the formation of bond between powder particle and annihilation of pores. The sintering pores can be divided into three stages: formation of neck, broadening of neck, and grain coarsening. Then the enclosing of spheroidization of pores. In case of biomaterial fabrication, sintering is usually finished in the second stage because the pores are interconnected. Porosity, pore size, and shape can be adjusted by size and shape of initial powder or by sintering condition, that is temperature, time, and atmosphere. Hot isostatic pressing (HIP). HIP consists in pressing of the object by hot inert gas. It is often used to densification of cast material. However, it can be also used for fabrication of porous materials. The combative powder has to be put into plastic capsule or called pre-pressed. The microstructure of the final material is influenced by size and shape of the initial powder particle and HIP parameters such as temperature and pressure. After the process, the capsule material is removed by machining. HIP has been successfully used for preparation of porous titanium and its alloy for for preparation of porous and nickel titanium shape memory alloy.
Spark plasma sintering process. This relatively new method allows use to very high heating rates, 102 to 103 degrees Celsius per minute, which prevents grain coarsening and decomposition of metastable phases. Powder is pressed in a graphite die with two graphite punches connected to a DC power source. This source works in a pulse regime. The DC pulses heat and batch very quickly. The most significant increase of temperature takes place on particle surfaces, while particle cores remain relatively cold. This leads to fast conduction of particle and limits changes of a microstructure of initial powder. The fine-grained or metastable powder can be fabricated by rapid cooling method or high-energy milling and mechanical alloying. SPS also allows fabrication of composite material like titanium or manganese-based alloys reinforced with hydroxyapatite. SPS is usually used for preparation of material with density close to their theoretical density. Reactive sintering means preparation of new phase or ordered solid solutions from two or more initial elemental powders. The mixture of elemental powders can be treated by conventional powder metallurgy, HIP or SPS. The driving force of the process is significantly stronger than in case of non-reactive sintering. This because new thermodynamically more stable phases are formed. The phases are formed around contact of two different metallic particles. The newly formed phase usually deteriorate diffusion of elemental metals leading to heterogeneity of the products. The products of reactive sintering contains two types of pores. Type 1 pores originating from imperfect compaction and sintering. Type 2 Kirkendels which are formed due to the difference in diffusion coefficients of metals. The main advantages of this method are that it prevents contamination by crucible material and allows preparation of phases with high melting points. The method has been studied as an alternative for preparation of nickel titanium shape memory alloy. Self-propagating high-temperature synthesis (SHS) is used to solid-state diffusion to obtain local eutectic or peritectic compaction of subsequent formation of liquid phase at temperatures lower than melting points of initial materials. Due to capillary force, the liquid penetrates through pores and react with unreact region forming new phases. This leads to another temperature increases and the temperature may reach values higher than the initial preheating temperature and even than melting point of initial pure component. The product of SHS are usually more homogeneous than those of reactive sintering. It is used for preparation of porous nickel titanium shape memory alloy. Impregnation of polymer formed by a metallic slurry. Firstly, a polymer form, usually polyurethane with suitable structure, is prepared and soaked with suspension slurry of fine metallic powders. Excessive suspension is pushed out between two rotating rollers, resulting in polymer form coated with a thin layer of the slurry. The suspension is subsequently dried. Polymer form thermally decomposed and the obtained metallic body is sintered. The product possesses high levels of open porosity. This method is very universally and usable for all metallic material. This method was used for preparation of porous titanium and titanium-based alloy. Forming of metallic powder. This method consists in forming of metallic powder using precursors of example polyurethane form. The precursor and metallic powder are mixed and a form is prepared. Polyurethane is thermally decomposed and metallic body is sintered resulting in highly porous open-celled structure. This method was used for preparation of a titanium form. Space holder technique. This relatively simple technique consists in a preparation of mixer coating metallic powder and powder of foam removal material spacer. The mixture is pressed into green compact and spacer particles are removed by leaching, evaporation, or thermal decomposition. The obtained porous body is sintered. Amount, size, and shape of pores are close to those of initial spacer particles. It is used for preparation of titanium and magnesium-based porous material. Advantages of biomaterials are it has high material strength and it is easy to fabricate and sterilize. Materials are non-toxic and it have high corrosion resistance. And the material also is biodegradable material. Disadvantages of biomaterial are they are aspectic loosening material, excessive elastic modulus, leachable in body fluids. The materials are very expensive and laborious manufacturing methods. Applications of biomaterials. Biomaterials are usually used in medical industries for the production of orthopedic implants, screw, pins, and plates. Bioactive orthopedic implants, dental implants, artificial hearing aids, dental filling, drug delivery system, porous orthopedic implants. Conclusions are conventional powder metallurgy and pressure assisted methods. HIP and SPS are suitable rather for preparation of materials with low porosity and small pores. Impregnation of polymer formed by a metallic slurry, forming of metallic powder or space holder technique are suitable for preparation of materials with high amount of large and interconnected pores. The methods allowing preparation of alloys and new phases from elemental powders, reactive sintering, and SHS can be modified in both ways to obtain material with low or high porosities. Biomaterials are primarily used or adapted for applications in the medical industry. This material contains a whole or part of living structure or biomedical device that leads, increase or replace the natural function of a body. Biomaterials are also used daily across applications for dental, surgical operations, and for delivery of drugs. There are different types of biomaterials available and each of them is used for various applications across several industries.